In our mission and vision, instilling excellence in electrical profession, having a dynamic professional association, making innovative contributions to our nation.
Hello everyone. Once again, good day to everyone. This is Professor Roger Flores, Associate Professor 4 of the Department of Electrical Engineering of Central Mindanao University. The professor of this subject, EE 41, Electrical Circuits 1. Okay, today we are going to discuss Chapter 4 of our subject. This is entitled Ohm's Law and Kirchhoffs Laws. Okay, to start with, to discuss this chapter 4, this is the chapter where we are going to discuss the most basic law of electricity, the Ohm's Law. And we will know later that this Ohm's Law was formulated by George Simon Ohm. And these Kirchhoff's laws are both Kirchhoff's current law and Kirchhoff's voltage law. This is another basic laws was formulated by Gustav Kirchhoffs. Okay, some faculty, some professors read this one as KIRCHHOFF'S, but I used to pronounce this as Kirchhoffs. Okay, so this is the content of Chapter 4, Ohm's Law. You have the Kirchhoff's law, current law, then you have Kirchhoff's voltage law, then the work and energy, and then work and energy, power dissipation and rating of circuit components, and then we have the efficiency. The last will be the kilowatt hour or the energy consumption per households, no, or per appliance. Okay, so here we are going to discuss the how you are going to compute, how you're going to more or less estimate our consumption, no, household consumption. Okay, so we have here to discuss. We have here the Ohm's law. Okay, so we have that as I mentioned a while ago that it was formulated by George Simon Ohm, and he said that the current is proportional to the voltage and inversely proportional to the resistance. So more or less, this Ohm's law here will discuss three factors. No? We have the current, voltage, and resistance. Okay. What are the relationship between these three parameters of electricity? The voltage, the current, and the resistance. This is what George Simon Ohm tried to share to us. No? Okay, so based on this statement of the Ohm's law, the formulated law of George Simon Ohm, we converted this into formula in mathematical expression. That is where I is, we have here I is equal to V over R. Okay, so where your I is the electric current, V is the voltage, and resistance R or R is the resistance. Okay, so this graphical presentation might help us on how you are going to remember this Ohm's law. Okay, so you have here the pi. Okay, this is represented by a pi. We have this blue color here, We have V, the voltage, the green color here part is your current I, and then the R, the yellow here is the resistance, no? So I hope that you will be able to familiarize, no? Now later on, why is that this pi here uh, is divided in this manner? Okay, because later on we will know that V over I is equal to R, or V over R is equal to I, or I times R is equal to V. That is the modified formula according to Ohm's law. Okay, so try to apply that graphical presentation to an example. So we have this. Okay, so for this given circuit below, we have this circuit here. For the voltage and resistance given in the circuit, you have the voltage is 100 volts, resistance is equal to 20 ohms. Okay, so try to determine the current I, this current here. So this current is just simply equal to V over R, or that is simply equal to 100 divided by 20, or that is equal to 5 amperes. Okay, so that is for example number 1. How about this example number 2? How much current will flow through 10 million ohm resistor when 50,000 volts are applied? Okay, so this is given in the again in this circuit diagram here. We have the voltage source, we have the current flowing in the circuit, we have the resistance, no? So okay, so just transfer to the other side. So according to the formula of the Ohm's law, which is equal to V over R, the voltage divided by the resistance, our given voltage is 50,000, and then our given resistance is 10 million. So more or less we have current is equal to 0.005, or simply equal to 5 milliamperes. Okay, in our previous chapter or previous discussion, we have these prefixes. No? So we discussed the prefixes. So we have this M, a small letter M is milli. So that is 0.001, or that is equivalent to, for this given example, we have this 5 milliamperes. Okay, so next we have this example number 3. So what if we have this circuit? How much voltage is needed to produce 5 amperes of current? So as you can see here, our resistance is 100 ohms. Our our current is given by 5 amperes. So this is 5 ampere here. So we have this one. So according to Ohm's law, where if your voltage is your unknown, this is just the product of the current and the resistance. So that is why we have this 5 times. So we have this 5 for the formula, 5 times 100. So that is more or less equal to 500 volts. Okay. So that is all about Ohm's law. I hope that anyway, I know that in your your high school, your senior high school, I think, or in your physics, you have discussed already this voltage, current, and resistance. So this is just a sort of recap or reprising your idea about the Ohm's law. So that is just a simple example of the Ohm's law. So next we are going to discuss the Kirchhoff's current law. And according to Gustav Kirchhoff, that the summation of currents entering a node is equal to the summation of currents leaving on that node. Okay, so that is how Gustav Kirchhoff stated his current law. The summation of currents entering to a node is equal to the summation of the current leaving to this node. So for example, if this is the node, then the current that will enter to this node is equal to the current leaving on this node. Okay, so the summation of the current at any point or any junction is always equal to 0. Okay, so let's try this presentation here, no? So this is the what we okay, so that is what we consider as a node here, no? So this is a node. Okay, by the way, a node or a junction is a point where there is two or more connections. Okay, there is a connection more than two or more connections. That is considered as a node. Okay, so as you can see in this presentation here, okay, so we have how many currents? We have five currents. Okay, we have five currents, and then we have current I sub 1, we have 5 amperes. I sub 2, we have the 2 amperes. We have this I sub 3, we have 4 amperes. I sub 4 is 2 amperes, and I sub 5 is 3 amperes. Okay, so as you can see the direction of the current as it is presented by an arrow, your I sub 1 is entering to that node, your I sub 2 is leaving to that node, and your I sub 3 is leaving to this node, and then I sub 4 is also leaving, and I sub 5 is entering. So more or less, as you can see, we have only two currents entering to the node, and we have three currents, I2, I3, and I4 leaving to that node. So if you're going to solve or have a summation of the current entering and leaving to that indicated node, then we have this, it should be equal to 0. Or that is that is given in this presentation, that summation of I entering node is equal to the summation of I leaving to that certain. So as you can see here, the current that is entering to that node is 5 amperes for I1 and 3 amperes for I5, then equal to the I sub 2, 2 amperes, plus I sub 4 amperes, and I sub 4 is 2 amperes, then it has a total of 8 amperes. So as you can see, current entering to that node is equal to the current leaving to that node. So it's just very simple. No? So anyway, let's continue with this example number 4. As you can see in example number 4, how many currents that we have? Okay, so it seems that we have three nodes, as you can see here. This one here, and this is this one here. But this is just an exaggerated illustrations. But more or less, these three nodes can be combined into one. Okay, so it could be combined into one because we don't have any other resistor here in between these three nodes. So just now try to imagine that this three nodes is only it is only represented by a one node. Okay, so how many currents entering to this combined node here? We have 3 milliamperes entering. You have 6 milliamperes entering. We have 1 milliampere entering. And we have 4 milliampere here leaving. And for another 4 milliampere leaving. And then we have this 2 milliampere leaving. So if you're going to solve for the solution, then it will be this one, no? So we have 3 milliampere plus 6 milliamperes plus 1 milliampere is equal to the leaving currents. We have 2 milliampere plus 4 milliamperes and another 4 milliamperes, and it is just equal to 10. Okay, 10 milliamperes. Entering to that node, combined node is 10 milliamperes, and leaving to that node is also 10 milliamperes. So that is an application of the Kirchhoff's current law. For example number 5. Okay, so this is another simple example. So this, you can see here two nodes, and between two nodes it has a current I sub 3. Okay, so we cannot combine this because current here is different, or it is you call this one? It is given current of I sub 3. Okay, so we have that I sub 3, no? So how here we are going to consider two nodes, node A and node B. Okay, so we have this node A and we have also this node B. So first, let us try to consider the first node, the node A. Okay, so at point A, then we have this expression. Okay, I sub 1 entering to that node A is equal to I sub 2 plus I sub 3. The two currents living on at node A. So node 1 is, or current 1 is equal to 2, current I sub 2 is equal to 3. So therefore, if you're going to solve for current I sub 3, which is the unknown on this part here, it is equal to I sub 1 minus I sub 2. So therefore, your current here is equal to negative 1 ampere. So meaning to say that your current I sub 3 is equal to negative 1 ampere. No? So do not be problematic about this negative 1 ampere here, because this is just a matter of the direction of your current. So as you assume here that your current I sub 3 is from node A to B, so of course since this is negative 1, then just reverse the direction. In actual flow of the current I sub 3, it is not from A to B, but it is B to A. Okay, so at point B, we have also three currents. We have the current I sub 3 entering to B. We have the I sub 4 leaving to that B. And we have I sub 5 leaving also to that point B. So what is now your equation according to Kirchhoff's current law? Entering is I sub 3 is equal to leaving I sub 4 plus I sub 5. Okay? So I sub 3 is equal to I sub 4 plus I sub 5. Okay? So that is why we have here. So since our unknown now, because I sub 3 was already computed or determined, our unknown now is your I sub 5. So your I sub 5 is equal to I sub 3 minus I sub 4. So we solved in the first solution I sub 3, so we have that minus 1. Then our I sub 4 is 6, so we have minus 6. Therefore, your I sub 5 is equal to minus 7a. So actually, again, I sub 5, the negative 7 of I sub 5 will tell us the actual direction of your current I sub 5. Therefore, the actual direction of I sub 5 is not away, but it is towards, okay, so at node B. So this is not away. So this is going to node B. Okay, so that is the actual direction of your current I sub 5. Okay, so let's continue our discussion with this Kirchhoffs Voltage Law. Okay, just to recap, the current Kirchhoffs Law is that according to Gustav Kirchhoff, it is the summation of the current entering to that node is equal to the summation of the current leaving on that node. So therefore, the summation of the currents at any junction or any node is just equal to 0. And this time, let us discuss Kirchhoff's voltage law. And this Kirchhoff's voltage law, let us start with this circuit here. Okay, so we have this circuit. So we have this circuit here. So as you can see, let us assume the direction of the current. It is from negative to positive in a given voltage source. So therefore, we have a clockwise direction. So clockwise directions, we will be able to determine the Kirchhoff's voltage law, because accordingly, according to Gustav Kirchhoff, that the summation of the voltages in a closed loop, summation of the voltages in the closed loop is equal to 0. Okay, so summation of voltages in a closed loop is equal to 0. So meaning to say that the voltage rise at the source, okay, the voltage rise at the source is equal to the sum of the voltage drops. Okay, so that is what we mean by summation of voltages at a closed loop is equal to zero. Okay, it should be closed loop. Otherwise, if there is something somewhere here in the circuit open, then this Kirchhoff's voltage law is not anymore applicable. So the applied voltage of a series circuit equals the sum of the voltage drops across the series elements. Okay, so this is what we said a while ago, that the summation of the voltage rise, which is from any sources, is equal to the summation of the voltage drops in any of the circuit. That is Kirchhoff's voltage law. Okay, so let's try this example number 6 now. This is a series. So even though we did not yet or we did not yet discuss a series circuit, but just to give a simple application of this Kirchhoff's voltage law, then we have this uh, circuit here. We have resistance 1, resistance 2. We have the voltage 1, we have the voltage source 2, E1 and E2. So even though the terminal polarity here is not given, but as we agreed in our previous discussions that the shorter horizontal bar is negative and the longer horizontal bar is positive terminal for this DC or the polarity. So therefore, the flow of your current here is clockwise. Okay, so this is the positive terminal, then our resistance. Okay, so this is nearer to the positive terminal. So this is the terminal voltage, positive. This is the negative terminal voltage, negative here. We have the other side. Okay, this is the positive, and we have this the negative, the other side. Okay, so just observe the flow of our current. Okay. So, according to the Kirchhoff's voltage law, that the summation of all voltages, voltage sources, and the voltage drops are equal to zero. So, start here. This is from negative to positive because we assume that the flow of our current here is clockwise. So, this is from negative to positive. So, that is why we have here positive. Then we have here positive to negative at resistor 1. So we have here negative V sub 1. We have this positive negative flow. We have negative V sub 2. And then this terminal here is positive and below here is negative. So positive to negative, that is minus E sub 1. And that is equal to 0 according to Kirchhoff's voltage law. So if you are going to substitute the value, okay, so our voltage A sub 1 is 16. By the way, our unknown here, our unknown is the voltage resistor or the voltage drop across resistor 1, V sub 1 here. So try to rewrite the equation. We have V sub 1 is equal to A sub 1 minus V sub 2 minus A sub 2. So therefore, our voltage drop across resistor 1 is 2.8 volts. Okay. Next, we have here number 7. We have determined the unknown voltage for the network of figure below. So as you can see here, we have a terminal between these 2 points here. Okay. So this is what will be the unknown voltage, no? This between these 2 terminals here, the positive terminal and the negative terminal. So as you can see here, how we are going to determine the voltage drop of V sub x here. So what we are going to do, try to imagine that we have a what we call this one, voltmeter. Okay, so insert a voltmeter. So try to insert voltmeter. So we have that, no? So by the way, before that voltmeter was inserted, this is the negative terminal. We have the positive terminal here. So we have that. We inserted the voltmeter. So now, if you are going to analyze the left side of the voltmeter, this is a closed loop. Okay, and the right side of the voltmeter now is another closed loop. So we are going to determine the V sub x here using individual loop. Okay, because we are only to consider only a closed loop. Okay, so we have here at this left side, no? Consider the left side of the loop of the voltmeter V sub x. So we have here using the clockwise path, including voltage source E, we have this will results to. Okay, so we have this voltage positive E. Okay, we have a negative V sub 1, and then this is positive here, we have negative here, so we have negative V sub x. That is according to Kirchhoffs voltage law. This is equal to 0. So if you are going to solve V sub x, then that is equal to the source voltage E minus V sub 1, the voltage drop across resistor 1. So we have that 32 volts minus 12 volts, and then that is more or less 20 volts. Okay. So what if we are going to consider the right side part of the voltmeter? No. So consider the right side. So let us now try to apply again the Kirchhoffs voltage law at the right side of the voltmeter. We have to start here with V sub x. So from negative to positive, so that is why we have this positive x, V sub x, minus the voltage drop across resistor 2, and this is minus positive, negative, so minus resistor resistance or voltage drop across resistor 3. So as you can see here, voltage drop across resistor 2 is 6 volts. Voltage across resistor 3 is 14 volts. Then if you're going to solve for V sub x, that is 20 volts. So as you can see, we tried to determine that V sub x here is also equal to 20 volts, either in the left side of the circuit or the right side of the circuit. So anyway, as you can maybe remember in your physics, that this V sub x here will result to a parallel connection of this left branch circuit and parallel connection to the right branch circuit. Example number 8. Okay, so example number 8 here, we have no, 2 loops. So we have loop number 1, we have loop number 2. In loop number 1, we have voltage source of 25 volts, loop with the terminal voltage of V sub 1, and another voltage source of 15 volts. And for this loop number 2 here, we have voltage 20 volts source here, and then we have the voltage V sub 2 terminal voltage. So our problem here is to solve for V sub 1 and V sub 2. Okay, so using path 1, the upper loop, so we have this plus, no, this is a minus plus, so we have this plus 25 volts. This is plus minus, so this is minus V sub 1. This is minus plus, so this is plus 15 volts. So 25 minus V sub 1 plus 15 is equal to 0 according to Kirchhoffs voltage law. Try to simplify, then we'll be able to solve for V sub 1 is equal to 40 volts. Okay, so for this loop number 2, okay, so from here, let us start here with this terminal voltage V sub 2. So this is clockwise, so we have positive to negative, it will result to negative V sub 2. And then this is also from positive to negative, so that is minus 20 volts. So more or less, your V sub 2 is equal to minus 20 volts. Again, do not be confused with that minus 20 because it just means that the loop or the direction of our loop is not clockwise, but it is rather counterclockwise. So that V sub 2 is now equal to positive 20 volts. Okay, so that is example number 8. So example number 9. So another example here, another circuit illustrated to us using block diagram. So we have the voltage source of 60 volts. We have another voltage load here. Block maybe it is it represents an appliance or a load, 40 volts. We have V sub X, the unknown voltage of the second uh, block, no? Then we have this 30. But of course, careful with the polarity, given polarity. Okay, so careful with the given polarity. You have, if you're going to assume clockwise direction, so we have positive 60, you have negative 40, negative V sub X. But take note of this block here, that is equal to minus 30. So minus plus, so meaning to say that this will become a positive 30 volts. Okay. So applying Kirchhoff's voltage law, we have 60 minus 40 minus V sub X plus 30, that's equal to 0. Try to rearrange our equation. Solving for V sub X, our V sub X is now equal to 50 volts. That is Kirchhoff's voltage law. Okay, so let's proceed to the work and energy. Work and energy. This is talking about electrical work and electrical energy. Okay, so before that, we have this definition. Work is done when a force acts to the certain body. Okay, so there might be work will happen or done if there is force, a certain force exerted to a certain body. So if this is a body, then we have the force applied to this body, and then this body will move, and then because of that, there is what we call as work done because of this distance due to this force applied. Okay, if the force and the body's direction are perpendicular to each other, no work is done. So meaning to say that if the force and the body are perpendicular to each other, okay, we don't have work done. Okay, so that's it. No, the unit of the work is joules, or having a simple a capital letter J. So another thing, talking about work, it will result to an energy. Why? Because as we defined, energy is the ability to do work. Okay, so basically in our physics we have the two types of energy. We have the kinetic energy and we have the potential energy. So what is that kinetic energy? It is an energy possessed by the body by virtue of its motion. When there is a motion, a kinetic energy is now produced, no? But if it is by virtue of position, no motion, at steady states or steady state, then we don't have the energy that we have there is the potential energy. Okay, potential energy. So work is performed when mechanical energy is converted to its electrical energy. When there is mechanical energy converted to another form of energy which is electrical, then there is what we call as work is produced. Okay, so we have this generalization. No? 1 joule of electric energy is required to raise 1 coulomb of electric charge through a potential difference of 1 volt. Okay, 1 volt, 1 coulomb of charge, then we have 1 joule of electric energy required to move this 1 coulomb of charge. Okay, with this equation, no? So 1 joule of energy is equal to 1 coulomb of charge and 1 volt of 1 volt of voltage or potential difference. Okay. By the way, Sometimes voltage, we call this one as potential difference, especially if this voltage is it is an electromotive force if it is in the source. But if it is between two terminal, that is potential difference, or just simply difference in potential. No? So between two terminals, if you're going to measure two terminals here, if you're going to measure the voltage between these two terminals, then it is most proper and precise to call this one as potential difference rather than electromotive force or just simply voltage. Okay, so the energy is now equal to Q times E, or the column of charge Q times the voltage of volt E. Okay, so that is W is your energy in joules, and Q is the charge in coulomb, and E is the potential difference in volts. Okay, so now let's continue to power. Okay, power is the rate at which work is done or energy expended. So how much energy is expended? So the rate of work done is called energy. So that is, from there we will be able to solve for the power. So power is measured in joules per second, and it has a unit in watt or kilowatt for a bigger value of your power, or megawatt, so on and so forth. So we have that unit of power is in watt. So we have another generalization here. Try to memorize these generalizations. We have 1 watt is the rate of doing work when 1 joule of work is done in 1 second. 1 watt is the rate of doing work of 1 joule energy or work in is done in 1 second. So that is your electric power. Okay, according to that, because of that generalization, then we will be able to write it in or express it in an equation form. So your P, your power, is equal to your work done per unit time or per unit seconds. Okay, so we have this formula: P is equal to W over T, where P is your power in watts, your W is work in joules, and time in seconds. Okay, so that is the formula of solving power, electric power. Okay, so the unit watt was originated in 1782. Okay, that it was from James Watt, who developed the steam engine. James Watt developed the steam engine because, according to the history, that there is water well, then uh, James Watt tried to convert the effort of this horse, which is used to pump or bring the water up. Okay, bring the water up. He is basically using the horses, and he converted this power of these horses into the what we call as a steam turbine or a steam engine that will pump the water from the water well to going upward. Okay, so he was the one who developed that steam engine, no? And then that is why, because of his contribution, the unit of electrical power is taken from his family name Watt, or from James Watt. So power may be expressed in foot-pounds per second, or they call this one as horsepower. So layman's term horsepower is caballo, no? Caballo. Horse is caballo. So maybe you might heard a common people will call this one as, okay, what is the power, the how much pila ka kabalyos is your engine. Okay, caballos is a Spanish term for caballo or horse. So that is why we have the unit of the machine power, which is called the horsepower, the power of the horse. Okay, so 1 horsepower is equivalent to 550 foot-pound per second. So foot-pound per second. So that is 1 horsepower. So that is the unit of the mechanical unit of power, no? Horsepower. Equivalent to 550 foot-pound per second. And if you're going to convert that to give relations with the electrical power, then that is 746. So take note of that one. No? 1 horsepower is equal to 550 foot-pound per second, or 746 watts. Okay, so we have this 1 watt is the power expended when 1 ampere of direct current flows through a resistance of 1 ohm, and that is our generalization with the relationship between the power, the current, and the resistance. Okay, so from previous equations we have is equal to W over Q, or the energy per unit charge, and then the current also according to our physics, that is equal to Q over T, or the charge per unit time. So if you're going to relate these two equations and multiply this voltage and the current, that is equal to your voltage and the current is equal to W over T. And take note that W over T is your power, P. So therefore, the unit of the power, electrical power, is E times I, or just simply equal to the power is equal to the voltage times the current. Okay, so that is okay. So let's remember this one. This is now the unit of your power. The electrical power is now equal to the voltage times the current. Okay, so later on we can have a modified formula of the power because we have the Ohm's law. It will help us, no? So what if resistance is given? So what is now E if given is resistance and current? So we will be able to modify the formula of your power. Okay, so can be obtained in two other forms from Ohm's law. So that is what I mentioned here. So for example, if the given is voltage and resistance, okay, so what is I? That I is equal to E over R, so that is why you have this E squared over R. So this is an modified formula. Okay, so next we have here uh, if the given is current and resistance, so we have another modified formula. We have I squared times R. So these are some of the modified formula of the power. Again, from A times I, we have A squared over R, or I squared times R. So we have that formula. So next, we have to continue to... Okay, so we have this example. So example number 10. What is the... Example number 10. What is the power delivered to DC circuit when the input current is 8 milliamperes and the supplied voltage is 24 volts? So as you can see here, we have two given parameters, the current and the voltage. So the current is 8 milliamperes. So what I want you to always note is you should have a consistent unit. Do not forget it. So we have 8 milliamperes, and then we have the 24 volts voltage. So what is now the formula that we can use to solve the voltage or the power? So it will of course useful formula here is I times E, or E times I. Okay, so we have this for our solution, A times I, 24 volts times 8 milliamperes. So that is why we have 192 milliwatt or 0.192 watts. Okay. So example number 11. What is the resistance of the device dissipates 5 watt of power when 30 volts is applied? So the resistance is our unknown, and the power is given with the voltage applied. So therefore, we will be able to modify our formula from P is equal to E squared over R, or simply our unknown is R. So R therefore is equal to E squared over P. So substitute the value. We have 30 squared divided by 5. More or less, we have the resistance dissipates power of 5 watt is equal to 180 ohms. Okay. Now let's continue our discussion with this power dissipation and rating of circuit components. So circuit components. What are some of the circuit components? Basically, of course, lamps, our appliances, our load, and but of course we have the resistance. Okay, resistor will produce heat, so it power dissipated on this resistor. So there is what we call as conversion of electric energy to heat energy. Okay, so more heat, more dissipated, more power loss. So just let's try to remember that one. All types of the circuit components are rated for a maximum wattage in terms of current and voltage. Okay, maximum watts, no, that is very important. It should be rated by for its maximum wattage or in terms of current and voltages. Okay, generally a safety factor of at least 100% is used when determining power requirements, no? So for a circuit components. Okay, so 100%, huh? So try to remember that one. When a resistor wattage rating more than 2 watts are required, then wire wand resistors are often used. So wire wand resistors. Anyway, we will discuss this more, no? And I think we discussed this in previous discussion, chapter 3 about resistors. So here the wire wand resistor is applicable if we need to have a 2 watts resistors needed. So these resistors are made in ranges between 5 watts to, okay, so we have that 5 watts and 200 watts. Okay, so that's it, no? Okay, so let's try this example number 12. The maximum current expected to flow through a 1 kilowatt resistor is 20 milliamperes. Okay, so we have this 1 kilowatt resistor, and then the expected current that will flow to this 1 kilowatt resistor is 20 milliamperes. So determine the wattage rating of the resistor using 100% safety measure or safety factors. Okay, so the given is current, given is resistance of 1 kilowatt, current is 20 milliamperes. So more or less the power is more 400 milliwatt or 0.4 watts, no? So 400 milliwatt. So what is now the rating of the wattage rating of our resistors? Sorry, our resistors. So basically, we have okay. So we have this 100%. So our power according to our solution here is 400 milliwatt. So 100% or just times 2 of our computed power. So that is more or less 800 milliwatt or simply equal to 1 watt. So 800 milliwatt, or it is okay, just round it off, and that is simply 1 watt resistor is required. Okay, so that is if we are talking about safety factors. Okay, so efficiency is a measure of how completely the power put into a circuit is used as output. Okay, efficiency is okay, how completely the input power uh, to make it output power. Okay, the input and the output. If you're going to see the difference, then the relationship between the input power and the output power is now what we call as percent efficiency. So to discuss, to go deeper with our discussion, so we have this. Okay, there is a substantial amount of input power is lost as waste or waste heat. So while we discuss power, it is sometimes in a form of heat. So because of this heat, there is what we call as a lost energy. So therefore, for whatever the input power, then we have this output, then there might be some losses within the process. Okay, so that is we are going to consider that losses. So that is why we have this formula of the power input that is equal to power out plus the power losses. This is the power losses as we go along with the conversion of the input to output power. So there is what we call always as losses. So what is now efficiency? It is the ratio of useful output energy to the total input energy. So output over input, that is your efficiency. Okay, so we have that. Okay, so it is expressed in this equation. So this is your efficiency, that is equal to your power output. Okay, power output divided by the power input times 100, that is your percent efficiency. Okay, so we have this. Your power here is are all in watts. Okay, so we have this example number 13. Okay, determine the efficiency of circuit that has a useful output power of 15 watts for its 20 watt of input power. So as you can see here that we have 15 watts for in output power. Our input is 20. So more or less there is how much? 5 watts lost. Oh, okay. So therefore to solve for our efficiency, the power output is equal to 15. The power input is equal to 20. Therefore, our efficiency is just equal to 75%. So the conversion of power input to power output, you have only 75% converted energy or power. We have this another example number 14. A motor has an efficiency of 85%. What current does it draw from a 120 volts source when its output is 3/4 horsepower? Okay, so let us try to analyze the motor, electric motor, and then the terminal voltage is 120 volts source. That is the one voltage source. Then the output of our motor is 3/4 horsepower. Okay, so our problem here is what is the current? Okay, so let us now try to determine the we have the power output is given 3/4 horsepower. So let us now try to determine the power input. Then we have this 85% efficiency. So let's try to solve for the power output. Okay, so power output now, because it is given in a horsepower, so convert that to and electrical power. So we have the factor of 746. So more or less 3/4 horsepower times 746 is 559.5 watts. Okay, so power input. Okay, so power and input according to our efficiency formula of efficiency equal to power out divided by the efficiency. So we have that 559.5 divided by 85%, so 0.85. So that is more or less the power input is equal to 658.24 watts. So we have this power input. So from this power input, we will be able to solve for the current if we have 120 volts. So how much current as it is asked, no? What current does it draw from a source of 120 volts? So your current is equal to P over E. Your power is 658.24 divided by the voltage 120. So your current is 5.49. Okay, so next let us discuss about the kilowatt hour. This is now the energy. Okay, the kilowatt hour or watt hour. So kilo meaning this is a prefix means 1000, no? 1000 watt hour. That is the energy. So this basic unit of electric energy is watt hour. So watt hour or electric energy is equal to P times T, or the power times time. So meaning to say that electric energy is equal to the product of the power and the time. Okay, so the electric energy is in watt hour, the P is in watt, and then your time here is in seconds. Okay, so watt hour meter is an instrument. Watt hour meter, no, is an instrument used to measure our supplied energy. Talking about electrical energy, our meter that we are going to use to measure the energy, electrical energy, is watt hour meter. Okay, so let us try this example number 15. So a generator delivers 4 kilowatt to a customer for 60 hours. So we have the generator. Take note, class, that generator is a machine that produces electrical energy, or it is a machine that converts mechanical to electrical energy, as we said a while ago in our discussion with this energy. Okay, so how much energy does the customer receive in this time? Okay, so again, we have the generator of 4 kilowatt output, and then it delivers the energy to the customer about 60 hours. So from the to determine the energy delivered to the customer, then we have this formula that energy is equal to power times time. So we have 4 kilowatt times 60 hours. So we have that 240 kilowatt hour. So that is how simple is that. Okay, so example number 16. Okay, so we have the cost of the energy. So this is very low, no? This time it is about 11 or 12 kilowatt, 12 pesos per kilowatt hour. I am not so sure, but this amount is very small. So anyway, for the sake of computation, we have 3.85 pesos per kilowatt hour. So that is the cost of energy, no, per kilowatt hour. So 3.85, 3 peso and 85 cents. So per kilowatt hour, how much will it cost to use a 60 watt lamp for 20 days? Okay, so what we have here is the amount per unit per kilowatt hour, per unit energy. And then you have the power of our lamp is 60, and then we assume that the observation is done, or the operation is done within 20 days. So our solution here, okay, so as you can see here, we have the cost per kilowatt hour. Okay, so we have 60 watt our power of our lamp, And then we have number of days. We have in operation, we have 20 days. Okay, so that this day will be converted to number of hours. Okay, because we have the kilowatt hour, unit hour here. Our day is converted to hour. So therefore, we have this conversion factor of 24 hour per day. So we have this days here will be cancelled. Okay, so we have this 60 watts and we have this 3.85 per kilowatt hour cost per kilowatt hour or per energy. Now is that this is divided into 1000 because our unit here is in watts of your lamp, and our cost per kilowatt hour is in kilowatt. So you have to divide this watts by 1000 to make this 60 watts to kilowatt, okay, unit. So again, try to have this solution, use and be always consistent of our unit. Okay, so just a computations, just using your calculator, then more or less for a 20-day operation of 60 watts lamp at 3.85 pesos per kilowatt hour, you will cost 110.88 of your electrical energy. Okay, so that is how you're going to compute the cost of energy. Okay, so I think that's end our discussion class, and hopefully you learned many things, no, in this chapter 4. Okay, so that's all. Thank you very much, and until next video. And if you think that you learned things about the discussion of this chapter 4, the Ohm's Law and Kirchhoffs laws, then try to subscribe my YouTube channel and click the notification for more videos in the future. Thank you very much. God bless and keep safe.
We are one in mission and vision, instilling excellence in electrical profession, having a dynamic professional association, making innovative contributions to our nation.